All right, thank you very much for the introduction and also the invitation to this very special occasion, I guess. Although I feel a bit daunting because I'm a theoretical physicist, and I usually don't give talks in front of biologists and mathematicians, but maybe this is the whole idea of this initiative. So let's see what I can do. So I understand that the audience is quite broad, so let me start with a very broad sort of introduction to the world of subatomic physics. So this is going to be let's say it's a public lecture level of kind of talk. So I hope it's not going to be so boring for you. And then I move on to the QCD, the quantum chromodynamics. This is theory of the strong interaction, which is I'm mostly concerned about as a nuclear physicist. And then I introduce you to the future experiment in the United States. It's called Electron-Ion Collider project. It will be a decades-long project, large-scale experiment in the US, and then which has a very broad scope. However, because this workshop is focused on this chirality, I will give you some selected topics related to the chirality associated with that can be explored at this electron-ion collider. So that's my plan. So let me start with the sort of mundane questions. What is the smallest unit in nature? So I start with a human, which is about 1 meter. And I take this as a reference scales, and then move it down. So let me first move down in 6 orders of magnitude, jump into the world of cell and bacteria. So this is a typical size is like micrometers. It's 10 to the minus 6 meters. That's the usual size of this object. And then further you go down by 3 orders of magnitude, and that reaches to the nanometer scale. It's 10 to the minus 9 meters, and that's the world of molecules. So what is shown here is the diamond molecules, and then further go down one order of magnitude. That's the angstrom. It's 10 to the minus 10 meters, and that is basically the typical scale of the atoms. And if you further go down 5 orders of magnitude, it's 10 to the minus 15 meters, called femtometers. That's the physics I'll be mostly focusing on. This is a physics of the atomic nucleus, and also the proton and neutron that is the building blocks of this atomic nucleus. And one can actually go down several orders of magnitude further down. You can reach that scales experimentally, but beyond that, almost nothing is known. And some people speculate that if you go down to the extremely small value of 10 to the minus 35 meters, then that is called the Planck scale, where the gravity and the other forces are unified. But this is a realm of the string theory, but not much. Of course, you cannot reach it in experiments. So I'll be focusing on this femtometer scales, the 10 to the minus 15 meters. And then there is this nucleus. So let me give you a little bit of a story of the discovery of the nucleus, which was done by Rutherford in 1911. So what he did is basically bombard a gold foil with a beam of alpha particles, the alpha particle being the helium nucleus. And then what he observed is that most of the time, this alpha particles passes through, so nothing happens, it just passes through. But sometimes it bounces back 180 degrees. And that was a groundbreaking observation. This means that there is a small and hard core inside an atom, and that is a discovery of the gold nucleus inside the gold atoms. So borrowing his words, what he said is that it was quite the most incredible event that has ever happened to me in my life, that it was almost as if it's almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So that was a surprise that that was his words. So that was a discovery of the atomic nucleus, and then the same person, Rutherford, discovered the proton in 1919, and his students, Chadwick, discovered the neutrons in 1932. And these are called, so the proton and neutron, these are called the nucleons, and these are the basic building blocks of the matter, accounting for 99% of the mass of the visible universe. Maybe I should emphasize the word visible, because in fact, the 95% of the universe, the mass of the universe is not visible. This is called dark matter and dark energy, which we don't know anything about it. But only the 5% of the mass of the universe is visible. In the sense, visible here means that they interact with the ordinary, interact with the ordinary forces, the known forces. And this 5%, so 99% of this 5% is accounted for by the mass of the proton and neutron. So these are the fundamental building blocks of the visible universe. And we want to understand its properties from the fundamental level. By the way, of course, Rutherford got the Nobel Prize for, however, he didn't get the Nobel Prize for this. And in fact, he got the Nobel Prize in chemistry before the discovery of this atomic nucleus. And after the Nobel Prize, he discovered the nucleus and he discovered the protons. So he could have gotten 3 Nobel Prizes. He's just such a giant. All right, so we know a lot of properties about the protons, but for example, we can measure the size of the proton. And this was first done in 1950, led by this Robert Hofstadter. So what he did is electron scattering. So you have a proton target and send an electron beam and see how this electron beam scatters. And you measure the angular distribution of the scattered electrons. And from that experiment, so this is a probability of scattering as a function of the angle of the electron scattered electron. And from this curve, you can infer the size of the proton. So this is measurement. This is the first measurement of this sort. And from that experiment, he found this value. It's 0.8 Fermis, which is, so I remind you that Fermi is 10 to the minus 15 meters. And that's basically how the size of the proton is determined. Nowadays, so this kind of experiment continues even now, 70 years after this first experiment. And nowadays, we know the value to 1% accuracy. So this was the first measurement, and we know the value at 1% nowadays. And one important message from here is that the distribution of the scattered electron is different from what you expect from the elementary particle. So if you assume the proton to be an elementary particle, then from that you see a deviation from that assumptions, which means that the proton is not an elementary particle. In fact, it's a bound state of quarks and gluons. So the proton, so here's a cartoon, the proton. So basically, there is a even smaller unit than the proton and neutron. So proton and neutrons are not elementary particles. Proton is basically the bound state of 2 up quarks and 1 down quarks. This is called the baryons. And the neutron is the bound state of 1 up quark and 2 down quarks. And the up and down quarks, they have different fractional electric charges. And so these 2 are called baryons. And there's another class of strongly interacting particles called the pions, the mesons. And this is a bound state between 1 quark and 1 anti-quark. So every single particle in the elementary particle has antiparticles. So that quark has an anti-quark, and this is a bound state between quark and an anti-quark. So these are called hadrons. And basically, the quarks are glued together by particles called the gluons. So this bound state is formed because of the existence of another particles called the gluons. And those are basically the mediator of the strong interactions. And this strong interaction is really strong. It's short-ranged, but it's really strong. And it overcomes the Coulomb repulsion to bind the nucleons and the nuclei. So there are, if you send these 2 quarks at a very short distance, there will be Coulomb repulsions. But since the strong interaction is so strong that it overcomes the Coulomb repulsion and realize these bound states. All right, so this is just a cartoon, but one can formulate this problem very precisely. This is basically the quantum chromodynamics, the QCD. So this is mathematically, this is a gauge theory, the so-called gauge theory, based on the color SU3 group. And this is the Lagrangian of the QCD, which is just one line. So this F is this is like a electromagnetic field, but this is a field strength tensor of the gluons. It's very similar to the QED, but it's a QCD version of this field strength tensor. And this Q is a quark, and the quark comes with different flavors. So there is up quark and down quark and strange quarks, and also there are heavier quarks. And each flavor of quark comes with 3 different colors. So up quark can be red, it can be green, and can be blues. And the interaction between quarks and gluons is dictated by this Lagrangian, which is constrained by the gauge symmetry. So you have interaction between quark and gluons, and also the self-interaction between gluons. So what is unusual in this Lagrangian is that this is written in terms of quark and gluons, but we don't measure these quark and gluons. We can never isolate on the quark and gluons. So what you measure in practice is called only the bound states of the hadrons, mesons. So this is so what you see in the Lagrangian is not what you see in the experimental detectors. So that is most mysterious part of this theory. So what's happening here is a so-called confinement of quarks. So as I said, the quarks are permanently confined inside hadrons. They cannot be detected in isolation. So here's what happens. So let's suppose there is this particle, this meson, it's called the J psi. This is the bound state of charm quark and the anti-charm quarks. So this is the bound state of C and C bar. And you want to isolate this quark. So you apply the force, you apply the external force, and you try to separate quark and anti-quark. So you pull them apart. Then at some point, some distance, then suddenly the pair of down quark and anti-down quarks pops up from the vacuums. And so then this down quark forms a bound state with anti-charm quark to form a meson. So one meson splits into 2 mesons, and you can never separate quark or anti-quark separately. So this is a confinement. This is what happens in. So you can never observe it directly, at least in experiments. And something very weird happens in this. Something very interesting happens. So there's the mass of the proton. So the mass of the proton is known. This is 938 MeV in this funny units. It's 10 to the minus 30 kilograms. But it's very difficult to explain this mass if you think of proton as a bound state of 2 quarks and 3 quarks, because the up quark, the mass of the up quark is 3 MeV, and mass of the down quark is 5 MeV, and the mass of the gluon is 0. So there is this funny formula that 3 plus 3 plus 5 plus 0 is 938. So that's what's going on here. So this is a very difficult mathematical problem. It's a $1 million problem, and when I say $1 million, I mean it. So here's there is a mathematical institute in Massachusetts. It's called Clay. So at the beginning of the year 2000, the new millennium, they announced the so-called Millennium Prize problem. So these are the 7 most difficult problems in mathematics at that time. And whoever solves any of these problems gets $1 million in rewards. And the number 1 is Young-Mills and mass gap. So this is the first of these 7 problems. Is called Young-Mills and mass gap, and this is roughly equivalent to making sense of these crazy equations. So that's a very difficult mathematical problem. And so this is not just a problem of physics, but also interesting problem of mathematics. Oh, by the way, so after 25 years, only one of these 7 problems has been solved. And this is it's called the Poincare conjecture, which I have no idea what it is, but this was solved by a Russian mathematician called Perelman. But he didn't become a millionaire because he refused the money. And he even refused the Fields Medal, which is an equivalent of Nobel Prize in mathematics. And the reason, this is what he said: I'm not interested in money or fame, and I don't want to be on display like an animal in the zoo. So he's the real scientist in this sense. Not interested in this thing. All right, so there is a mystery in the mass of the proton, and there's also another mystery in the spin of the proton. Maybe not as perplexing as the mass of the proton, but it's still considered as an interesting problem, at least in my community. So proton and the neutron, they are fermions. So they have spin 1/2 in this unit of h bar. It's a Planck constant. And so how do we explain this 1/2? Because proton is a bound state of quarks. So ultimately, this number 1/2 should be explained by combining the angular momentum of quark and gluons. So very naively, you can just get this 1/2 by adding. So two of the quarks have plus 1/2, and the last third quark has minus 1/2, and that's how you get this 1/2. This is a very naive expectation based on the so-called quark models, but usually, as a rule of thumb, quark model is very good. So probably in reality, this is roughly correct. That's the naive expectation. Now, you can test this conjecture by actually measuring this quark contribution to the proton spin, and it turns out to be only 30% of the proton spin is coming from the quarks. So this was taken as a surprise at the time. This experiment was done more than 30 years ago, and this number, 30%, still persists. So there is a bit of a puzzle here. How does the proton, where does the spin of the proton come from? So that means that it's not enough to consider just the spin of the quarks, but you also have to consider the spin of the gluon and also the orbital angular momentum of quarks and gluons. So there must be some orbital angular momentum of quark and gluon, meaning that quarks and gluons are orbiting inside protons. So there's a very complicated dynamics inside a proton. So naively, we expect that proton is something like this, just a 3 quark. However, it might be something much more complicated than this naive. So we want to understand this question. So then people ask, how are the quarks and gluons distributed inside a proton? So not just so what is the momentum distribution of these quarks, and what is the position coordinate distribution of these quarks and gluons, and how do they contribute to the mass and the spin and size of the proton? So these are the very interesting questions that we want to pursue. So we are going to build a detector. It's called the Electron-Ion Collider project. So this is the next generation, starting probably in the mid-30s, nuclear physics facility to be built at the Brookhaven National Laboratory where I work. So here's a EAC. So there is a ring accelerator, and my office is probably somewhere around here. And this is Long Island. So here's Manhattan, the famous Manhattan, and here there's the Brookhaven National Laboratory. And so this experiment will be starting in the mid-30s, so probably roughly 10 years from now. But already there's a lot of interest in the world, and so there's a ESC users group, and then there are more than 1,500 people registered in this users group from 300 institutions in 40 countries, even though we are still 10 years away from the experiment. And I think last year, Japan has also expressed interest in participating in this experiment. So this is an article from the newspaper. And I should say that, in fact, the Hiroshima group plays an important role because Shigaki-san, he's so the experimental group at the Hiroshima University is one of the first experimental groups to have expressed interest in EIC and actually joined the experiment. So this is I think it's a very smart move. So there's a lot of interesting in this future collider experiments. So here's quickly the main physics goals of the ESC, which was articulated in this National Academy of Science report in 2018. And the committee found the 3 most important questions to be addressed at the Electron-Ion Collider. Number 1, how does the mass of the nucleon arise? Number 2, how does the spin of the nucleon arise? So I already explained that. And number 3, I haven't mentioned it. What are the emergent properties of dense system of gluons? So if you accelerate proton to very high energy, then you generate lots of soft gluons, low energy gluons, and eventually they become a very dense system of gluons, and you want to understand property of this new forms of matter. But I'm mostly talking about this first 2 in this talk. So what we can expect is that the era of precision QCD study of nucleon and the nuclear structures in the next 20 to 30 years. So there will be exciting times ahead. So here's the experiment at the electron-ion collider. It's called the deep inelastic scattering. So I already talked about the elastic scattering to measure the size of the proton. That was elastic scattering. But now what we do is inelastic scattering. So the electron emits a photon, and the photon hits a proton, and the proton is basically destroyed and goes into a bunch of hadrons like pions. So this experiment was first conducted in the 60s at SLAC in the US, and this was actually led to the discovery of quarks. This is experimental evidence of the quarks, existence of the quark at the time. And then there was another follow-up experiment over the past many decades. And the most recent one is called Hera. It's an experiment at the German facility. And at the EIC, the frequency of the collision is 1,000 times higher than the previous what we had at the Hera experiment. And there are many important features. So this is going to be the first polarized electron-proton collider, which means so you can polarize the proton and both proton and electrons. By polarize means that I can orient the direction of the spin in whatever direction I want. So that's what I mean by polarize, and you can do that only at the electron-ion collider. And also, it's a first electron nucleus collider. So this target is proton, but you can also use any nucleus of your choice. So it can be proton, it can be deuteron or helium, or it can be also a very heavy nucleus like lead nucleus. Yes. So that's the experiment. So and here's microscopic, and you can analyze this process very precisely using the perturbation theory in QCD. And so the idea actually goes back before QCD. It's by the Richard Feynman, who observed that this process, you can think of proton as a bunch of free non-interacting partons propagating in one direction. So the photon hits one of the quarks and strikes it out, and then finally, eventually, lots of particles are produced. And this process can be analyzed using the perturbation theory of the QCD, that's the interaction that I already showed. And it is considered as the best tool to probe the internal structure of the proton and nucleus. So the EIC offers unprecedented coverage in kinematics, and there's a tremendous physics opportunities So there's a lot of interesting subjects that can be explored at the electron-ion collider. But today, because of the nature of this conference, I will be mostly focusing on topics related to the chirality, because this is what this audience is interested in. So I'll be only talking about a very small section of this EIC project, which is related to the chirality. So let me quickly remind you what is chirality in the context of particle physics. So, right from the start, let me say that the quarks are chiral, okay, in the sense that, so they can be right-handed or left-handed, in the sense that, so suppose this quark is moving upward in the screen, and this, when I say chirality, it basically means the helicity of this quark. So the spin of the quark can be in the same direction as the direction of the motion. That is called right-handed, or it can be opposite direction from the direction of the motion. That is left-handed. So the quarks are basically a chiral object. So you might immediately see the connection to this proton spin problem. So suppose you have the proton has a spin in this direction, but it consists of lots of quarks inside. And so whether the question is, in order to explain this proton spin, you basically have to explain the imbalance between the number of right-handed quarks or the left-handed quarks. That basically contributes to the total net spin of the protons. So it's very crucial to understand the issue of chirality to understand the proton spin. And the same is true for the gluons, because gluon also has a chirality. It can be right-handed or left-handed. For the massless particle, you can only have parallel or anti-parallel. That's the only possibility for the massless particles. Yeah, for the massless part, I neglect the mass of the quark here. And for the massless particle, the direction of the spin can be either parallel or anti-parallel. It cannot be transverse. The direction of motion. For the massless particle.
I mean, surely sorry, I just don't understand. Maybe I missed it. How can quarks be massless unless the nucleus is moving?
Well, the proton mass is, the quark mass is very small. As I mentioned, it's only 3 MeV. So you can approximately treat it as a massless particle. This is a very good approximation, by the way.
So, sorry, then, if I just can understand, then, what's its direction, which I think is the previous speaker, presumably there's no overall motion within the proton.
No, I am assuming that the proton has moving in the upward direction.
So it's just the motion of the proton?
Yeah.
Okay, sorry. Yeah. I apologize for
interrupting. No problem. All right, so there is a very deep connection between the spin puzzle, the spin puzzle and the chirality problem. So that's important to understand. And then there is also an orbital angular momentum. So how does the orbital angular momentum enter the game? So and there is an interesting development recently, which basically by my group at Brookhaven. So this is related to spin orbit coupling, which is probably very familiar to every one of you. For example, you know that there is spin orbit coupling in the hydrogen atom, so electron has spin and orbital angular momentum, and there is interaction between them. So that's a spin orbit coupling. It's a very universal and ubiquitous context phenomenon in all areas of contemporary sciences, and including in QCD, which is not discussed before. But so what is we observed here is a very perfect anti-correlation between chirality, which is same as spin, and the orbital angular momentum. So for the soft quarks and gluons. So this means that if the quark is right-handed, then the orbital angular momentum has to be -1. And if the quark is left-handed, then the orbital angular momentum has to be +1. So there is a perfect anti-correlation between the spin and the orbital angular momentum, and that's actually, this is a quantum entanglement. You can describe this situation as a quantum entanglement. So what is realized in the small x part of the QCD, the quark and gluon inside the proton, is basically every single quark and gluon at small x is a Bell state. So this is a maximally entangled state where you have a spin and orbital angular momentum always pointing in the opposite direction. And I was very excited that very similar phenomenon has been previously discovered in the context of quantum optics. So here's a paper published in Science in 2018 where they experimentally realized this maximally entangled photons. So here's a very interesting experiment. So you have a beam. You have a beam of linearly polarized photon, and this beam hits the material. It's a special material called the metamaterial, which I don't know anything about it. But in any case, when this photon comes out in the other side of this material, and this is maximally entangled in exactly the same way as I explained here. So this is a QCD analog of this, what happens in quantum optics for the photon. But in the case of QCD, I don't need this metamaterial. As soon as quark and gluon are generated at small x, they're automatically maximally entangled. So that's a very interesting feature, and maybe it's an interesting connection to interdisciplinary connection. All right, so that was the connection between chirality and spin. But I want to talk about chirality in a more general context in QCD, and that brings me to the notion of the chiral symmetry. Is the microphone working? It's not working now. Well, I can show. All right, so let me explain what's the chiral symmetry of QCD. So I'm coming back to this Lagrangian. It's just one line, and there is a quark mass term here, but I said the quark mass is so small that it's very good approximation to neglect this quark term. And then this QCD Lagrangian basically splits into the left and right. There is nothing that mixes left and right. So you have this quark term that splits into the left-handed quarks and the right-handed quarks. And there is no interaction between left and right at the level of Lagrangian. That means that there is a separate symmetry between the left sector and right sector. That is the chiral symmetry of QCD. So you can rotate these left quarks up and down strange. Left quark using this UN, the unitary matrix of NF. NF is the number of quarks. And you can also separately and independently rotate the right-handed quarks using a different matrix, still unitary. So there is a UN times UN chiral symmetry of QCD. This is a very well known. However, this symmetry is actually spontaneously broken. So this is a Nobel Prize work by Nombu. So the QCD Lagrangian is invariant under the chiral symmetry, but the symmetry is spontaneously broken in the ground state of QCD. So in the QCD ground state, you have this non-vanishing condensate, this is a non-perturbative condensate that mixes the right-handed quark and the left-handed quark. So this is the theories. The Lagrangian is symmetric even at the quantum level, but the symmetry is spontaneously broken at the level of the ground state. So there is this pattern of symmetry breaking. So SUN cross SUN breaks down into the diagonal SUN of quarks. And this is a chiral symmetry. This is a famous chiral symmetry breaking. And this chiral symmetry is a continuous symmetry. So it is a well-known fact that when the continuous symmetry is spontaneously broken, then massless particle emerges. And this is nothing but the pions of the strong interaction, which is almost massless. It's actually not massless because quarks are massive, but approximately you can treat it as a massless particles. That's the origin of the pion. So at the electron-ion collider, we can study the structure of the pion, which is usually not possible because pion is an unstable particle. So you cannot prepare the beam of pions, but you can effectively do this by using the so-called Sullivan process. So this is electron-proton scattering at the ESC, the electron-ion collider. This proton emits a pion, the pi plus. This is actually a virtual pion, and this virtual pion interacts with the photon and they produce the vector meson. So if you study this process near the threshold at the low energy, then you can study the so-called gravitational form factor of the pion, which is basically the matrix element, off-forward matrix element of the QCD energy momentum tensor. So if you can measure this form factor A and D, then you can study the internal dynamics of the proton because this energy momentum tensor, the different components of the energy momentum tensor has a different physical interpretations. For example, this energy density, you have a momentum density, and the shear and the pressure distribution. So you can study this distribution inside a pion if you study this process at the EIC. So actually I added this slide after listening to the first talk in this morning because the speaker mentioned the SKR model, so I thought this might be interesting to this audience. So the SKR model is nowadays is very famous in the condensed matter physics and mathematics, but it was originally introduced as a model of the proton, right? And after subsequently, people can develop the solution that correspond to the nucleus. So you can also model nucleus. For example, this is a proton, which is spherically symmetric, but this is a deuteron, it's a baryon number 2, which is, believe it or not, this has a donut shape, and this is a helium-3, helium-4, and so on. And you can also make very nucleus with very large baryon number, for example, this 108. So in this work, we studied the energy momentum tensor inside this nucleus, computed it. And for example, this is the pressure, the quote-unquote pressure distribution inside these nucleons as a function of a radius from the center of the nucleus. So the energy momentum tensor is actually a very hot topic in my community. So we studied energy momentum tensor inside nucleus. Well, coming back to the chiral symmetry. So this is the last topic on my talk. So I already talked to you that the SUN part of the chiral symmetry is spontaneously broken, but the original symmetry is UN, and SUN, there is a U1 factor is missing. So what happened to the U1 chiral symmetry? And it turns out that this is not a symmetry actually from the beginning, because even though this is a symmetry of the Lagrangian, it is explicitly broken by the quantum effects. So, and this is called the chiral anomaly. So if you calculate the divergence of this would-be conserved current, then this is the difference between right-handed quark and left-handed quark. This is supposed to be 0, at the level of classical analysis, but it's actually non-zero at the quantum level. This is called the quantum anomaly, and this is called, so F mu nu tilde, that's a Gouron contribution. So there is no symmetry from the beginning, so it cannot be spontaneously broken because there is no symmetry if you go to the quantum level. And as a consequence, there's no massless particle associated with the symmetry. And actually, there would be massless particle. It's called the eta prime meson, but it's far from massless. This is actually, it's as heavy as the nucleons. So what the consequence of this anomaly is that if you measure this matrix element of this operator, this actual vector operator, you have two form factor Gn and Gp, and these two form factors is a priori independent of each other. But it's actually, they are related because of this anomaly relation. So this anomaly relates form factor. This is a non-perturbative relation. So this has been known for many years, since the 70s. And what is new and what can be studied at the electron-ion collider is the non-local generalization of this chiral anomaly. So before I talked about this operator, the local, so these two quark fields are positioned at the same point. This is a Z here. But one can actually generalize this object to non-local direction. So Z1 and Z2, they are separate, actually. And even with this non-local operator, you still find anomaly in the, so if you compute the divergence of this non-local operator, then you still find anomaly if this Z1 and Z2 are related, separate in the light-like direction, in the sense that, so if you, so I'm using the relativistic notation. So this Z contains the time coordinate and also the space coordinates. So this Z1, so this square goes to 0 doesn't mean that the Z1 is equal to Z2. They can be far away as long as they are separated in this light-like directions. So you can generalize this chiral anomaly in the non-local way. And so here, if you compute the divergence of this non-local current, then you find the non-local version of this anomaly. So this is a new, this is something not many people know about it. So what is the consequence of that? So if you take the matrix element of this non-local object, then you find what is called as the generalized pattern distribution functions. So H tilde and E tilde, and this function basically tells you the spatial distribution of patterns and quarks and gluons inside the protons. So this is a very important object to study at the electron-ion collider. And like before, the anomaly relates these two generalized pattern distribution functions. So there is a non-perturbative relation mediated by this chiral anomaly, which relates this H tilde and He tilde. So there is a relation between two GPDs, which is mediated by the chiral anomaly. So that's pretty much it. So let me conclude. So the electron-ion collider, it's a major future direction of the nuclear physics in the US and around the world for decades to come. And the Hiroshima group is a key participant in Japan's experimental efforts. So I want to emphasize that. And finally, in connection to this initiative, the chirality of quark and chiral symmetry breaking played an important role in core scientific topics at the electron-ion collider. An example include the QCD spin physics and the GPD, but I would expect that there will be more connection that to be explored in future. So thank you very much.